Chapter 4.3, Other Bases. So in this chapter, we're going to start exploring the idea of using numbers other than 10, even in our current numeration system. So we've seen the positional values for the Hindu-Arabic system being 1, 10, 10 squared, hundreds, 10 cubed, thousands, 10 to the fourth, 10,000s, and so on. We've seen the positional values in the Babylonian numeration system, 1, 60, 60 squared, 60 cubed, 60 to the fourth, and so on. 10 and 60 are called the bases of the Hindu-Arabic and Babylonian systems, respectively. But any counting number that's greater than 1 could be used as a base, even if there isn't some ancient system that used it that way. So, if a positional value system has base b, then its positional values will be 1, b, b squared, b cubed, b to the fourth, and so on. For example, base 2 has 1, 2, 4, 8, 16, and so on. Base 3 would be 1s, 3s, 9s, 27s, 81s, and so on. So, where have we seen other bases before outside of just our exploration of history? Our society actually has remnants of, for example, the base 12 system, the duodecimal system. Anytime you think about the fact that there are 12 inches in a foot, or 12 months in a year, 12 items in a dozen, 12 numbers on a clock, the reason this 12 comes back a lot is because of the base 12 system that was used previously. We also have the base 60 sexagesimal system shows up a little bit, just like it did in Babylonian numbers. 60 seconds to a minute, 60 minutes to an hour. These are remnants of other bases being used besides base 10. But where do we see these other bases in more modern times, more explicitly? Computers, essentially. That's what we really need other bases for, is working with computers. So computers and other electronic devices make use of three specific numeration systems that aren't base 10. First one is the binary system, which is probably the one that you may have heard of. This is base 2. It uses only the digits 0 and 1. 0 and 1 represent essentially electronic switches within the computer, being off for 0 and on for 1. All computer data can be converted into a series of these binary digits, and each binary digit is then known as a bit. Once we get 8 bits, we can form a byte and convert into the octal base 8 system. Octal is used to form the American Standard Code for Information Interchange, which is ASCII. You may have seen that abbreviation before. So the ASCII code allows us to represent letters and like wingding symbols using a specific 8-digit code that gets transferred between computers so that every computer knows this represents the letter A. Even if it's in whatever crazy font we want it to be in, it's the letter A no matter what. So 01000001, that's the capital A, and 011000001 represents lowercase a. Then we have a step above that is the hexadecimal system. So this one allows us to have base 16, and it is used to create computer languages. So HTML, JavaScript, CSS, most computer languages use hex or hexadecimal a conversion in order to write out numbers and do coding, etc. So, all of these are heavily used in web page design, but any sort of coding you're going to run into hex, but especially with web pages. And, for example, colors are written in hex when they're translated through a computer, etc. So computers easily convert between binary, octal, and hexadecimal numbers, base 2, base 8, and base 16. But can we do that? Well, let's first start with bases less than 10. So a place value system with base B has B distinct symbols. one for 0, and one for each numeral less than the base. So remember, in our system base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 symbols. Notice that I didn't say 10 as one of the symbols because 10 is not one of the symbols. 10 is a combination of 0 and 1. So in the base 6 system, we have symbols for 0 through 5, and all numbers within base 6 are constructed with only symbols 0 through 5. The base 8 system has symbols for 0 through 7, and all numbers in base 8 are constructed with those 8 symbols. There should never be a number if you are converting into another base, that is B or greater, essentially. So that's one way to sort of check your work, and it's a very common mistake, is to leave 8s in our base 8, or put the number 9 there. Those don't exist within the base 8 system. Only 0 through 7 are allowed to be used, in the same way that we in base 10 have 0 through 9 as our symbols. We're not going to have a specific symbol for 10 because 10 is made up of 2 symbols we already have. So a numeral in a base other than base 10 will be indicated by a subscript base to the right of the numeral. So 1, 2, 3 with a little subscript 5 represents a base 5 numeral. 1, 2, 3 in base 5. 1, 2, 3 with a subscript 6 means it's a base 6 numeral. Notice that it's still 1, 2, 3, but they have completely different meanings. 1, 2, 3 base 5 is not the same thing as 123 in the base 10 we know. But when we write 1, 2, 3 with a subscript 10, we don't necessarily have to write the subscript 10. So if you see a number that doesn't have a subscript like this, you just assume that's base 10 because that's the default. That's the one we know. It's like writing a square root symbol. Square root is technically the second root, but we don't write that. Whereas if we were writing a cube root, we have to write the number there to indicate that's what it is. So the default is base 10, so we don't have to write it. But any other base, we have to note what base we're talking about so that there isn't any confusion. Now, how do we actually do the changes between bases? Essentially, the same way we did with our historical systems. We take our number in base 10 and multiply each digit by its respective positional value, then find the sum of the products. So, we can note that 1, 0 base B will always represent the base, e.g. 10 base 5 is 1 times 5 plus 0 times 1 equals 5. If n is a digit less than base B, then n base B equals the same thing as it would in base 10. So 2 base 4 is the same thing as just 2. So let's convert 3, 1, 2 base 4 into base 10. So we start out by writing out the positional values, the base 4 place values. That'll be 1, don't forget the ones, 1, 4, 4 squared is 16, and we actually only need 3 positions because there are 3 numbers here. So we place each number over its place value. 3 is the 16s, 1 is the 4s, 2 is the 1s, right? So we have one numeral in each, and we notice that these 3 numbers are all less than 4. So that's something we want to remember, is that they should be less than 4. Now we do our multiply, add, multiply, add, multiply. So 3 times 16 plus 1 times 4 plus 2 times 1 is our 3, 1, 2 base 4, and that is equal to 54 in base 10, which again we don't need to write, but just as a note. So 54 in base 10 is 312 in base 4. Now let's try converting a binary number into base 10. So to convert this binary number, we need to know our base 2 place values. And how many of them do we need to know? Well, we've got 1, 2, 3, 4, 5, 6 digits total, so we need 6 place values. That'll be the 1's place, the 2's place, the 2 squared, which is 4, the 8's, the 16's, and the 32's. Notice I go up to 2 to the 5th because we start with 2 to the 0 place. So 0, 1, 2, 3, 4, 5 gives us 6 positions. We'll know we have enough positions if we can make a position for each of our numbers. Just don't skip out on the ones place. I say this because it's very common to do 2 to the 6th place as a place and then not have the ones place, and you'll be pretty far off if that's what you do. So, we've got 1, and we multiply, times 32, add 1 times 16, add 0 times 8, add 0 times 4, add 1 times 2, add 0 times 1. So altogether, we get 50. So 50 in base 10 is equal to 110010 in base 2 in binary. So now you know how to convert numbers into binary. But of course, converting from base 10 into another base is the more complicated process, just like it was when we were converting with the Babylonian or Mayan numerals. So, step 1 is we divide the base 10 numeral by the highest power of the new base that is less than or equal to the given base 10 numeral and record this quotient. So, if I want to convert 273 into base 3, I need to think about my base 3 place values. So base 3 place values, I get 1, 3, 9, 27, 81, 243. 3 to the 6th power is in fact a little too high. So 3 to the 6th power, just as a note, equals 729, which is greater than 273. That's a greater than symbol. So we don't need that position. We start at 3 to the 5th power, 243. And so we will list out each of those positions and make sure we fill them all in. So 3 to the 5th, there are 243s, our 81s, our 27s, our 9s, our 3s, our 1s. I didn't really give myself enough space, but we'll need to fill in each of these positions by going through the process of dividing, finding the quotient and remainder, then take the remainder and repeat. So first step, I'm going to take 273 and divide by 243. 273 divided by 243 equals 1 with a remainder of 30. Now remember, how did we find that remainder before? We take this number, which again, it's technically 273 divided by 243 is, hold on, 1.1234567 It's very interesting. But we don't care about this part. We just know there's some remainder, and we need to find the whole number remainder that represents. So the 1 is the quotient, and so I take 1 times 243, and I subtract that from 273. So 273 minus 1 times 243 is 30. And so that's where we get that remainder. Now we take the remainder and we bring it to the next step. So 30 divided by 81 is, well, it's a little too high. So 30 divided by 81 will be 0.37, It doesn't matter. The point is we get a 0 here. And the remainder will be the full 30 because we didn't really remove anything. But just as a reminder of how we get the remainder, we take this number multiplied by this number and then subtract it from here. So that is 0 minus 0 equals 30. So now we repeat. We bring our 30 down, we divide by 27 now, our next position value. So 30 divided by 27 equals 1.11111, yada yada, we don't care. The 1 is what matters. The remainder is 3, and again, this is one where we've gotten to numbers where you might be able to figure this out without doing the multiply and subtract part. That, well, there's 1 times 27, there's 127 in there, and then there's 3 left over. That's what a remainder means. It's left over. So there's 3 left over when I divide by 27, because 27 plus 3 more is 30. But just to be very thorough, I take these two numbers and I multiply them. And so that'll equal 27, and then I subtract that from 30 to get 3. And now repeat. With my remainder, 3 divided by 9 this time, which again, 3 divided by 9 is going to be 0.33333, right? So we'll get a remainder of the entire thing because when we multiply, 9 times 0 equals 0, 3 minus 0 equals 3. So we keep our whole remainder and we go on to the next step. 3 divided by 3 equals 1 with a remainder of 0, because 3 divided by 3 is just 1 and there's nothing left over. There's no decimal position. So we can then sort of do that last part, 0 divided by 1 equals 0. Or we can just realize that once we get to the ones place, whatever that last remainder is going to be the ones position. So our place values end up being, again, I'll write them out, the 273s, 243s, I should say, 243s, the 81s, the 27s, the 9s, the 3s, and the 1s, which you should be keeping track of the entire time. So you can sort of write this out as you go. So first we get a 1, then a 0, then another 1, then a 0, then a 1, and the last one is going to be a 0. So all together we get 1, 0, 1, 0, 1, 0, base 3. Make sure to note that base so you're writing it in the right format. And then, of course, we want to check our answer by actually converting back into base 10. So that'll be 1 times the 243, right? We'll go back to this. 1 times 243 plus 0 times 81 plus 1 times 27 plus 0 times 9 plus 1 times 3 plus 0 times 1. All together, we get this, and it does, in fact, equal 273, which is what we're hoping for. So that tells us we did it correctly. But what about if I wanted a base greater than 10? Then what happens? So in our base 10 numeral system, we don't have singular symbols to represent numbers greater than 9. For bases greater than 10, we will need to come up with those single-digit ways to represent those numbers. Why is this? Essentially because if I write the number 10, it is the numbers 1 and 0. It is 2 position values. So if I want that to be 1 place, because I need to be able to use numbers up to the base, not including it, then I'm going to need a singular, in this case, we'll use a letter symbol. So whenever a base larger than 10 is required, we use the capital letter A to represent 10, B 11, C 12, and so on. Generally, it's like we go up to 16 with this most commonly. You can go further than that, but 16 is the most common base above 10 that we use. So, for example, if we have base 12, we use the symbols 0 through 9 and then AB, because this would be 10 and 11. Base 16 is then 10 for A, 11 for B, 12, 13, 14, 15. Again, like I said, we can keep going. We have 26 letters we can use. What do we do after we get to that 26th letter once we finish out with Z? Well, like I said, we don't talk about those systems as much, but we would have to define some new symbols, essentially. So generally speaking, that's not as useful, so we don't really need to talk about that. So we're just going to stick with the systems where we can use letters. So up through, I guess that would be, base 36 is as far as we can technically go, but we're really going to stick with these earlier ones, because once we get up in those numbers, it gets a little complicated. So let's try doing some conversions. So if I want to convert 7DE, which is in base 16, into base 10, we start by noting the powers of 16, the powers of our base. So 16 cubed is 4,096, 16 squared is 256, then 16, then 1. We need how many of these? Essentially, we only have 3 positions, so I'm only going to need 3 place values. So I'll have the 256 place, the 16's place, and the 1's place. And I just place each piece in order. Now we want to do our multiply and add, the same thing we always do, multiply, add, right? Multiply, add. But we'll notice that when we do that, we have letters in there, and that's, how do I multiply D times 16? Well, D doesn't mean D the letter. D represents the number 13. So we're just going to change that into 13 for D and 14 for E, and now we can do that multiplication and addition, and we get 2014. So now we've converted. To go in the other direction, it's still the same process. Even though it's a larger base, it's the same process we've been doing. So we look for what is the highest base, or highest power of our base that is still less than the number we're trying to convert. So for the record, 16 to the 4th power is a pretty big number. It's 16 to the 4th is 65,536, which is obviously much bigger than 6,713. So we don't want this. We're going to start with 16 cubed. So we will have position values for the 4096 place, the 256's place, the 16's place, and the 1's place. 4 position values we're going to need to fill out completely. We fill it out by starting with 6,713 divided by 4096. That will equal 6,713 divided by 4096 gives us specifically 1.6389 yada yada. I don't care about this part. Remember, what I care about is the 1. And then we find the remainder. It's a pretty big remainder, right? So I find the remainder by multiply and subtract. So when I multiply these together, it'll equal 4096. I subtract 4096 from 6,713, and I will get 2617. So now I take that remainder and I repeat. So I do 2617 divided by 256, because 256 is my next position. And that's going to equal 10 with some decimal places, right? With a remainder of 57. Once again, we get our remainder by multiply. So this will be 2560. And then I subtract 2560 from 2617, and I'll get 57. So, one note we have to make is that I don't like leaving this as a 10. We want to convert it. But as soon as we see a number that is 10 or greater, when it's got 2 digits, we need to convert it into its letter form. So that 10 will become an A. Then we take 57 and we repeat the process. So 57 divided by the next position value, which is 16, is going to be 3 with a remainder of 9. Again, we get that remainder by multiplying 16 times 3, which equals 48. Subtract the 48 from 57 to get 9. And now we repeat. 9 divided by 1 is just going to be 9 remainder 0. So we really, once we get to that 1's place, we can just know that it's going to be that number. So I kind of didn't write it here. But you can do that last one if you want to, just to, make sure. But we get 1A3 and then that 9. 1A3, 9, and we write the subscript 16 to say, yes, this is base 16. We've got our 4 numbers in our 4 positions. Again, making sure to fill out the 4 positions we did at the beginning. So the let's try that again. The 4096's place, the 256's place, the 16s, and the 1s. So you should note from the beginning how many numbers you're supposed to get. That way you make sure you do enough work to get all those numbers. Then we check our answer by doing the multiply and add. So multiply, add, multiply, add, multiply, add. 1 times 4096 plus A being 10. So 10 times 256 plus 3 times 16 plus 9 times 1. All that does in fact equal 6,713, so we know we've done it correctly.